So with this, I welcome Mr. Timo Haimi from Metso, Finland, and he will be talking about ferroalloys and DRI smelting. So the first,
Yeah.
yeah. So over to you,
Yes.
Mr.
Hello.
Haimi.
Hello. Hello. I guess you can hear me and see me. That's that's great.
Yeah, we can. We can.
All right.
Please
All right. All
continue.
right. Yeah. Thank you. Thank you. I'm very sorry that cannot be there with you because of these schedules here. But I have this presentation for you. What what we were. Yeah. So hello everyone. Nice to be here presenting. Last year I was in the same conference, also presenting remotely. So maybe next year we will be finally meet there in person. But thanks for having me there, and let's go this. So yeah, the topics are ferroalloys and DRI smelting, my two favorite topics because these I have been working here in Outotec and Metso. And first, quickly showing that who is Metso and what we are doing, and then in smelting, me and my colleagues in the smelting business, then the ferrochrome process, which is interesting for India especially, and then the DRI smelting furnace for sustainable iron production. And myself, like I said, Timo Haimi from smelting nowadays, working in the sales, but 15 years in Outotec and Metso, mainly with the ferroalloy technology and projects. So I've been in all kind of roles. 10 years in the process design and implementation of the projects, especially in the Chinese ferrochrome plants, and also living in the China in the Shanghai office. And yeah, and before that, before the time, my experience from the Finnish blast furnaces and the steel making plant and from the arc furnace in Finland. And for India, you can see that the ferroalloy projects are interesting, and this the DRI smelting as well. So let's take a look at those. And Metso, I guess everybody knows Metso in Finnish technology company, working in the aggregates business, minerals processing business, and myself and the colleagues we are in the metals refining. And I also presenting here from Espoo, Finland. And if you take a look at the Metso strategy here, these interesting topics here, the energy transition and the electrification. So it means you need a lot of metals. So we see that there we have many projects for copper, lithium, nickel. So that's everybody understands this one, and it's bringing a lot of possibilities for the minerals processing, but also for the metals refining. And then decarbonization of the steel industry. We have this our pelletizing guys from Germany. They have these pelletizing plants. They have been, and also from USA, this Great Kiln pelletizing plant. They are working in the India projects. Our German colleagues, they have the Circored hydrogen fluid bed direct traction technology there, which is very much interesting globally. Could be fitting for India as well. And then my own product is this DRI smelting technology, which means basically that we are melting the DRI and producing hot metal with our smelting technologies. And also we have the circularity projects everywhere, and could maybe mention the e-waste for Hindalco for the copper scrap. I mean e-waste recycling project. And then about the smelting business, what we have in mostly based in Espoo in Finland. We also have these teams in Sweden and in Australia. And we have these different technologies here. For example, we have this agglomeration, this steel belt sintering, which is need for chromite pellets but could be also fitting for the manganese pellets and some other. Then we have this flash melting for copper and nickel projects, or top submerged lands TSL projects from Allsmelt Australian team for different kind of metals. And then we have many different kind of electric smelting furnaces, DC furnaces for the fine materials, open slag bath furnace, for example, ilmenite smelting. Then we have these different slag cleaning furnaces in many projects. Submerged arc furnace, which is the solution for the ferrochrome production. Then the 6-in-line smelting furnace, which is for the DRI smelting needs. And mostly our projects, they have been focusing into all other metals, like I said, ferroalloys and non-ferros, copper, nickel, ferrochromium, PGM, ilmenite smelting, which is the titanium oxide slag. So these kind of projects have been doing, but recently, like I said, the DRI smelting has been interesting globally because blast furnaces needs to be replaced, or everybody's interested to replace them. Let's see when those are actually happening. But making sponge iron with the direct traction is possible. But how to get the material melting? If you have too much slag, arc furnace might be in trouble. So then we come to the smelting furnace area. So I have these slides about that. But first, let's look at this chromite, our Metso's Outotec ferrochrome process, which has the background in the Outokumpu times, when the Outotec and Outokumpu were the same company, nowadays part of Metso. But okay, small picture here, but this beginning we have the agglomeration, which means that we are making pellets out of chromite, or then we have a closed smelting furnace for efficient smelting process. And on top of that, we have the preheating kiln to boost up this closed furnace. And this closed furnace needs pellets. That's why we had the agglomeration. And we had these grinding mills, slurry mixing, filtering, make the filter cake. Then have the mixer and this drum pelletizing. Then we had this steel belt sintering. Okay, it's not actually sintering, it's induration, it's making hard, good quality pellets, but anyway, it's there. And preheating kiln to heat up the material before smelting. And closed melting furnace means that you are getting high quality, more than 80% carbon monoxide gas as a byproduct, clean it and use it as an energy for the preheating, and use it as energy for this pelletizing plant. And then still you have a 20 megawatts of extra energy, what you can heat up ladles, or you can create electricity, or different things. But the agglomeration plant here, I mean, making the pellets, it has like less than $20 per ton is the pelletizing cost here. And then it's very much boosting the furnace productivity together with the preheating kilns, which means that we can get this 3,000 kilowatt hours per ton of ferrochrome energy consumption or less. But of course, this depends what's the chromium content we are. So with the 50% ferrochrome, it's of course lower than with the more higher chromium content. But anyway, we are based on high plant availability, high production, less furnaces, bigger furnaces, continuous operation, highly profitable. And this is also example for this conference. Interesting is that we are making this kind of process for Fakor Ferroalloys Corporation in Part-2 in India, and ferrochrome product for Sukinda ores, and 300,000 tons of capacity EPS supply for technology package We have this 700,000 tons of capacity steel pen sintering plant for this Sukinda ore, and we have been making our own R&D test work in our pilot plant, and we are creating good quality pellets out of that material. Then we have this 2 times 75 MVA submerged arc furnaces with preheaters. And the project is going on, deliveries are going on, startup next year. And then hopefully in the next conference we can tell you more about this project, what's happening there. Delivery time 22 months, and it's looking okay. And while we are in this process, in the Outokumpu times, it was different process. We had this rotary kiln shaft furnaces in the 70s and 80s in the industrial scale production. Also made pre-reduction in the rotary kiln for many years, and but it turned out very challenging in the rotary kiln process. So it has been then developed in the 90s and continued further, this steel belt sintering plant, preheating kiln, and the smelting furnace, and it has been the most economical and the most productive solution. And why the pre-reduction is difficult? Well, we all know that carbon is very efficient in reducing chromium, and that's why we have been focusing into maximizing the carbon yield in the process. Because the natural gas testing, we have been doing a lot of testing, but it's challenging, the natural gas pre-reduction. And hydrogen, if you look at the Ellingham diagram, then you can see that it's a bit difficult or even impossible for the hydrogen to produce the chromium part. The iron part you can reduce, but if you have less iron, like in the Indian chromites usually have, it means that you have less reduction potential there because you are mainly reducing only the iron part. So yeah, this is a bit challenge in the pre-reduction part, and so therefore we are focusing into maximizing the chromite carbon efficiency in the chromite production, and which means agglomeration for the big smelters. You need good pellets, as you can see here. Those are the good chromite pellets. Then preheating kiln here, we are removing all the volatiles which would be otherwise be burning the carbon on the process. We don't want to do that. We want to use the carbon purposes and bring the energy with those electrodes, cerebral electrodes. And the closed melting furnace, we don't want the leakage air, ingress air to burn our valuable reductants, metallurgical coke. So that's why the closed furnace and this feed with the preheating. And we are all the time measuring almost 100% carbon efficiency for the process. So that's very good. And we have been doing tests with the bioreductants, but each bioreductants, they have their own challenges. Then you can replace from the coke, but it's not perfect solution. And then we look at this DRI smelting, what we are doing with the DRI smelting. This is the flow sheet for the iron, sustainable iron production, that you have this formatory handling, and you have blast furnace grade iron ore, not the high grade DR grade ore. Put that into the production plant, operate it with the natural gas or hydrogen, whatever you have available, and you can have pellets or you can have fines, depending what the process is. But the point is that you can take all of these shapes, grain sizes, and even the hot DRI here into the smelting plant. So we have 2 smelting plants here in the industrial concept here. We have 2 smelters, 1 million tons capacity each. So you are making this couple of million tons of molten green iron for further processing. And why it's said like this, it's because it depends on the carbon content, that what kind of a processing you need. Usually we are not in the same carbon level than the blast furnace, but we are lower levels. But it depends. It can be 0.5%, 2%, 3% carbon levels, depending what is the feed DRI carbon content here and how much we can carburize it here in the smelters. But the idea is that to have the slag product the same time with the blast furnace, so you can utilize the slag. And so commercial reference not yet done, but all the equipment references we already have suitable size. So the furnace is the 6-in-line furnace, and we have similar sized rectangular furnace from the flash smelters with the cooling elements for the walls and to the roof, and then electricity is coming from these Cederberg electrodes, which we already are making. Biggest one are 2.1 meter diameter. In this furnace we need only 1.5 meter, so it's okay, no problem. Gas cleaning, digital systems, and the capacity, like I said, why we need such big capacity is because the blast furnaces, they are huge. When the steel plants, they are replacing the blast furnaces, they can get this 2 million, 2.5 million tons DRI capacity if you put a big matrix there. Then you need 2 big furnaces for smelters to create the molten metal. And the difference with the arc furnace is that we are removing the slag, we are removing the gangue here without iron losses. We have closed furnace, no air ingress here. We have a highly reducing atmosphere here. So we are making the final reduction, removing the slag without excess iron oxide losses to the slag. So no iron losses here. And blast furnaces, they are the king of the steel making, iron making. They are continuous operating, highly productive. So that's what we want to, or we need to be there. High availability and long campaign lives for the refractories. That's why we have the cooling elements in the furnace to keep this system in place. And metal tapping to one side, slag tapping to one side. There are the 6 electrodes here bringing the electricity. These are the feed pins for the DRI and also for the reductants and the fluxes. You can modify the slag composition in the furnace, and you can do the final reduction and some carburization of the metal. And the beauty is that you can continue making the same steel grades than at the moment, because we don't need any scrap input here. You are not messing up your metal quality with the metallic impurities from the scrap. And to prove this to everybody, we have the R&D center in Finland, where we have the existing pilot furnaces, but we made even new pilot furnace, which is rectangular furnace, 3-in-line, 2.5 MVA transformer, 1 ton per hour capacity. And this one was here it is a picture. It's a beautiful plant. We made this internal EPC project in 12 months, and hot commissioning and the test work was done in this year, in this spring, and we had this 50 tons of test material, and that we also asking from the customers, because this is open for all customers who have this green steel, green iron DRI project. If you want to check how that lower grade iron ore DRI is working for the smelter, then please be in contact. Let's agree. Let's make this test work here and see how the furnace is working. But why we need so much material is because we have capacity. Smelting capacity is 1 ton per hour, so roughly you can say 10 tons per day. So you can have 5 days of pilot testing with this material. So, but if you think about the commercial size, you are producing like 120 tons per hour, so it's even bigger. But this system is working, as you can see. Good material flow, good molten metal flow. We had 2.5% carbon content in the feed DRI, and 2.5 was also in the product metal. So that was working well. Feed system working well, electrodes working. Yeah, everything was doing very well. We even tested the bioreductants briefly, but like I said, they are more challenging. They are more volatile in the bioreactant, so carbon yield was less. The material was burning a little bit too much. But anyway, let's continue the test work. And next one, what we are gonna do in this summer, we're gonna have this low carbon DRI. Hydrogen reduced DRI, but also the Indian rotary kiln DRI is also good for this purpose to see how that works. Because that natural gas based DRI that has 2.5% carbon, that is working well, is melting well, and everything is okay. But the lower carbon is interesting how it works. So thank you for this presentation. I think I was just in time for this slot, and please, now you can shoot some questions there.
Thank you, Mr. Jaime. Yes, you are just in time. And you have talked about the energy transition, the main problems in today's ferroalloy sector and steel sector, the decarbonization, because everybody is going for decarbonization and CCUS and other things, and the recycling. So if I will request if anybody want to ask any question to Mr. Jaime, so please you can ask.
Any question from the audience for this? Okay, I think we can have it later. If something, we'll send him, and thereafter we can connect. Thank you.
Yes, I have Sumit is there, my colleague, so Sumit can be the connect person there.
Yeah, thank you, Mr. Jaime.
Thank you very much. Okay. Have a nice conference. Thank you.
So our last presentation will be given by Mr. Sujit Sengupta from Canada, Admira, Canada and USA. And he will be talking about AI in hydrogen and CO2 integrated steel making. Very important presentation. Yeah, good afternoon, Mr. Sengupta.
Good afternoon. Good afternoon.
So your topic is, it is written AI in hydrogen and CO2 integrated steel making. So I welcome on behalf of Steel Tech, and you can start your lecture.
Thank you. Good. Thank you. Can you hear me? Thank you. Can you hear me?
Yes, you are audible.
Okay. Thank you very much. Thank you, distinguished guests and organizers, for giving me this opportunity. So we will talk about a few use cases in AI and hydrogen use in steel making, and we'll also talk about the SMRs and the applications in data centers and things like that, and then cryogenic energy storage and distribution. So I'll just share my screen.
Yeah, we can see you, Sujit. Yes, your slides are visible and we can hear you properly. Please go ahead. Thank you.
Okay, so basically, I am the president of Admira Distributed Hybrid Energy Systems. We are based in Canada and the US. So it's a research-focused, technology-oriented company. We work in green hydrogen, cryogenic technologies, and to improve the viability of technologies in the industry. We last time I presented in the conference, I shared the use of hydrogen in the hydrogen train in California. So as you know, in 2028, the California will host the Olympics. So they are upgraded their capabilities, and one of them, they're implementing the hydrogen train and the Los Angeles metro system, which will connect the hotels with the airport and the stadiums. So that's in electric light railway projects, and then green hydrogen technologies, that's where we work in. So we try to integrate technologies, need to connect hydrogen producers and consumers. We have capabilities in terms of liquid hydrogen, liquid oxygen, electrolyzer, design, storage, robotics, controls, process modeling, and project management and AI. We'll share an a use case on that in a mine, in a large nickel mine. So we work a lot on safety and hydrogen, and then servicing the heavy industries in terms of decarbonization initiatives and turnkey project management. So we partner with a company in California, Soteria Companies, which was set up in 2002. And we work on hydrogen safety, system safety, additional safety services, security safety, and equipment safety. Security in terms of safety of equipment, not security per se. So we try to improve the accessibility of technology to liquefiers, both small and large, medium hydrogen and oxygen generators, because as you know, electrolyzers, they generate both oxygen and hydrogen. So oxygen could be a very important byproduct in the steel industry to use. So we have project management capabilities, and I'm running through the slides. With quite a few slides, but we will share the slides with the audience. And so we try to offer customized solutions, collaboration with several vendors, and including the leading players in cryogenics, and we can leverage our capabilities in US, Canada, and Europe. Europe, we did a project study and a pilot for cryogenics and liquid air storage in Sweden. And in Canada, US, we are trying to do the light rail systems we did in Edmonton, and we are now doing in California and Los Angeles. So this is a rendering and this picture of a modularized cryogenic liquid air energy storage system, or which, and an ASU for which we are working with the Department of Energy in the US to design a pilot for a data center. And this is what we did in Sweden. This is, we used a cryogenic storage power recovery system together with a fuel cell system and a hydrogen system. And basically, we try to service heavy industries. As we know, heavy industries, including steel, is hard to decarbonize. So we try to develop projects where we can decarbonize the heavy industries and transportation. Then coming to steel, like steel industry emits around 7% of the global CO2. And large steel plants are BOF and blast furnace routes. And hydrogen can partially replace coke, emitting hydrogen and CO2, distinguished gas here, we all know that. And then we can use a CO2 recycling to reduce the emissions. And mini blast furnace are one of the ways where we have tested, as we will see. So in Canada and the rest of the world, electricity is clean and cheap, and so we are following the electric arc furnace route. But for India and other developing countries, the DRI route and the blast furnace route is still viable, and the injection of hydrogen is something we should look in. And also cleaning up the coke oven gas, as we spoke in the last conference, and using hydrogen from coke oven gas. So we have seen some pilots happening in Japan, in Germany, in India, and China. So they have been able to reduce fuel by 30%, 20% CO2 reductions in a 400 meter cube blast furnace in China. Some projects in Nippon where they use Nippon Steel, where they able to reduce 43% of the CO2, and in Germany where they injected hydrogen. So now one of the things is CO2 we can capture in the gases, and then we can have a carbon capture and storage system. And Mittal is in Europe, is doing a pilot in converting the captured CO2 gas into ethanol. And in US steel, and US Steel is trying to capture the CO2 and use it for cement production. So these are the projects which are happening. And this is a thing of direct interest to me, direct reduction production of steel, and Romelt is a very promising technology in this, where we can use hydrogen and CO2, and here we don't need coke. So coke we can use non-coking coal. So this is a very promising technology if we follow the DRI Romelt route with the use of hydrogen and CO2 with synthetic syngas. So there has been some pilots in Russia and India. In India, NDMC tried this, but this becomes a very promising technology in terms of the use of hydrogen and DRI route to steel making. So one of the things is the cost of hydrogen. So green hydrogen becomes viable at around $2 a kg, and but we have to also have to factor in the cost of carbon capture and CO2 capture. But it leads to 50% reduction in CO2 and reduced emissions of SO2, PM, and NOx. And then Romelt is a lower capex and modular versus the blast furnace and the Corex routes that we have followed before. And especially if we want to integrate, have a free trade with the European Union, then these things become, and still in view of the tariffs and all the negotiations going on, green steel is viable. So one of the things and challenges is the thermal management of the blast furnace if you follow the blast furnace route, and then the material durability, because of hydrogen makes steel brittle, certain types of steel brittle, and then the O-rings and the gaskets brittle. So we'll have to, that's one of the challenges when we convert a hydrogen, a blast furnace or a DRI system to use of hydrogen, to a mixture of, we can up to 20-25% is reasonable and feasible, but after that we have to do some changes in terms of the metallurgy of the components. And so they can, from all the studies that we have done, we can reduce emissions by 20-50%. And then, as I said, that Romelt offers a scalable, low carbon iron making for diverse regions. And so for DRI, where DRI is a very important pathway in developing countries like India, and as opposed to EF, where electricity is cheap and green in the developed countries. So one of the things that can happen, I said that is that we can clean up the coke oven gas in my earlier presentation, and coke oven gas in a mixture of hydrogen, methane, carbon monoxide, and carbon dioxide. So this gas can be cleaned up and hydrogen produced, then used, so that downstream we don't have emissions. So this is like we will need a pier to clean up sulfur, ammonia, tar, and then have a PSA to clean up the gas. We should have the carbon capture system. So these are things that we should consider and look into in our design of a new green steel plant. So one of the things that I mentioned last time also, I just want to go through, is that the CO2 can be used with argon in the AOD and VOD in system, reducing iron consumption and having us a good handle on controlling the temperature of the burden and the use of the system. So we see if we use CO2, then there will be some savings in terms of argon usage, and then we can control the decarbonization rates. Then this just showing you AI system, a design system that we have done for a steel plant in terms of software development, where we use an electrolyzer, a fuel cell, hydrogen and oxygen from the electrolyzer, and renewable power for the electrolyzer, and we model the plant for a steel mill. Now, just changing gears a little bit, we were fortunate enough to work in a underground mine, very harsh conditions in the Arctics, and use AI for electric truck maintenance. And this is very feasible also in open cast mines. So if you want to reduce the emissions and carbon footprint. So Volvo has done use cases where they've reduced by 20%, and we worked in Canada in Coleman, a nickel mine in northern Ontario. In Sudbury, the Corona trucks are very proven electric trucks. Okay, so basically we had the opportunity to work with AI and electric truck maintenance in a mine in northern Ontario in Sudbury. And we have been able to increase the availability from 75% to 83%. And this is a very harsh environment, cold, very cold underground mine. But the same thing can be utilized in open cast mines where you have a lot of transportation of ore. So we use natural language processing, and we use the data from the sensors where we created a digital twin, and then we used it to help the maintainers using the DMAG technology concepts and the RCA concepts to increase the availability of the trucks by 27% and the ton mile coverage by 9.6%. So what we did is we analyzed the sensors and the historical data, the failures, and we were able to create a high uptime, which is very important for in a mining or steel operation. So as I said, that cost of downtime is very high. So in open cast or underground mining, and it's a huge amount of revenue that is lost, about $1.4 trillion by the top 500 companies of the world. So it is certainly something which is very attractive and feasible. So this is a little bit of the detail that how do we analyze. We use the DMAC principles, we divided the components, created a hierarchy, and then AI is a game changer because it allows us to do proactive maintenance and use natural language processing as well as thermal imaging and computer vision capabilities for inspections. This we also used in our hydrogen train in California. So this is a little bit of the details we created. If anyone is interested, we can go into the details. Like we used the Corona truck, divided it into subsystems and organized it in such a way that it will be amenable to natural language processing and AI. So we can through AI we can analyze photos, thermal images, wear and defects, automatic checks on the brakes, tires, connectors, etc. So it increases the accuracy and it predicts. So this is a electrical hierarchy system of the truck that we created. This is the failures that we had in the trucks, the drives, the collectors, transformers, motors, and midship. And then this is the truck itself divided into the components where failures had occurred and how we increased the availability to 88% from 82%. And we used natural language programming, which helps very here to find out hidden patterns and maintenance weeks in advance. So it really helps us in the maintenance. So we were in the process, in this project, we were able to increase the availability by 27%, and we were able to create predictive models, and we were able to push the availability to beyond 90% as a potential. So another thing that we are trying to do, and we are working with the Department of Energy in the US, is modeling small, medium reactors and for base load power and integrating it with renewable energy in a microgrid. So, but this technology is being developed to going through the regulations and the safety systems being developed. So it is a projected to come into online in 2030, but in between now and 2030, we have to have technologies and microgrids available, as I will show in a few slides, that we can do this. And the Department of Energy has is evaluating a pilot that I will show it in a minute. So basically, this slide is very important. Like, we can create a microgrid with based on various renewable technologies and SMR, and we can have it operate within the grid with a high degree of availability and reliability. And we can then synchronize with the grid with protections to protect the microgrid. So this is a very important concept which we are working on. This is the project that we are doing for a pilot project that we are doing with the Department of Energy in the US. We have just submitted a proposal. We take green electrons, convert in hydrogen, use the electrons to convert hydrogen in the electrolyzer and oxygen. We store hydrogen as liquid, and then in the process we use the waste heat and cryogenic energy storage to regenerate energy as well as use the waste heat. And we did this concept we are doing this for a data center, but it can be easily utilized in a steel environment. And then, as I was saying, that the SMRs are not available till 2030 in terms of all the implementation. So we could integrate hydrogen and fuel cells to take us through that phase. So, as I said, that baseload power and net zero and clean grids and very stable grids, these are the advantages of SMRs and microgrids, including hydrogen and fuel cell in this slide that we are developing for the Department of Energy. And so now there are some doing it. Amazon is doing, Dow in Texas is doing it. So these are the projects that are being developed. So the hurdles are the regulatory hurdles, the licensing hurdles, the safety hurdles, the contracts, construction risk, and upfront cost. So here there is a scope for a hybrid system. One of the companies that they are working is on, Bloom Energy is working on solid oxide fuel cells, and we are working on hydrogen-based electrolyzers. So these things, we can go for a hybrid model with present-day technologies till we have better scale developments of SMRs. So the outlook is that governments, federal regulations, important, purchase power agreements are important, and today we are working with data center with pilot SMRs because the demand is huge in terms of electricity and AI. But the same can be applied, the same technology can be applied to steel making. So this is the last slide. I run through them because there are lots of slides, and that the data center market itself is $517 billion by 2030 because of the use of AI. So, and AI will be very much used in operations, steel making, and all the big manufacturing setups. So we are talking of 200 terawatts of energy that will be needed. And out of that, it is very interesting to know that 40% goes into cooling systems. And India is a hot country. So this I'm talking about cold climate. So India, the demand of cooling will be very high also. So integrated systems using waste heat is something which we should certainly look into. So my slides are finished. I hope I did not take a lot of time, and then I will take the questions now. So I'll stop sharing.
Thank you, Mr. Sengupta. Really, you have talked about the two most important buzzwords of this particular time, that is artificial intelligence and the sustainability based on hydrogen. Actually, for India, in particular this steel sector, what I feel that we have now, we are going to the coal gasification system, the CO2 generation from coal gasification to the steam reforming. We are now producing hydrogen using actually we are using the black hydrogen and gray hydrogen and brown hydrogen, but we need to go to blue hydrogen first, where we have to do the CCUS, because in today's perspective, in Indian context, green hydrogen, production of green hydrogen is really costly. But definitely, using your expertise and whatever you have shown that in Canada the electricity cost is very less. So hopefully in India also one day electricity cost will be less, so that we can produce the green hydrogen in the most energy efficient manner. So I request the audience, if you can ask any question. If you have any question, you please ask Mr. Sengupta.
Thank you. Thank you.
Yeah, thank you, Sujit. Excellent presentation. This is Pritish here. And you know, when we discussed about some research thing, what you are mentioning, if it is some scope with having a joint here in Indian thing, you can mention a bit. What is it possibility?
Yeah.
That's what I said. Yeah.
Yeah, so just like we are doing in the US, Canada, and Europe, we are doing pilots and testing out systems before we build the full-scale models. So the Department of Energy, the National Science Research Council in Canada, we are working with them. A similar model, like if we can get a good partner in India, a similar model we could do work with Indian research institutes and develop a pilot and develop a design, a feasibility study, and then prove the system. So this is certainly possible in India. We are exploring that, and we'll be more than happy to work at it and see what are the funding avenues to do such a design, a feasibility, a pilot. And this doesn't have to be a high cost project. We can start small. That's our, like we are very nimble. So we can start small and then build to a bigger project. So this is always feasible, and we welcome any interest from India for sure.
Thank you, Sujit. I think you can tie up with some our research institute as well as some industries, so that we can take it forward. And when you visit to India, we can take it, or we are here as a partner, we can carry on and proceed.
Yes. Yeah. We will be very happy to partner with the Steel Tech's ecosystem of experts that you have, and institutes that we have in India. And we are very much bullish about working with like an industrial partner and a research institute. So it's just not the research institute. We should have a strong industrial partner and together with the research institute, and then we can work on it.
Yeah, thank you. We have a very strong team here, where the people who are in Steel Tech generally having a very good background, and they have industry background. They have worked for several years, and there are people also in the Steel Tech editorial board who are in the educational institute like IIT Jadavpur, KNU, and other places, and also research unit and technology developer as well. So we can take it forward. Thank you very much for giving the insight. Thank you. Thank you. You got an excellent presentation. Yeah. Thank you. Thank you,
I
Sujit.
just have one question.
Some more question.
Sir, I'm Preeti Chatterjee from Plumule Research. I just wanted to see your the truck hierarchy slide once. I just missed it.
Okay, just a minute. Okay, just a minute. I'll share the screen.
You'll
Just
be
a
sharing the presentation, right, sir? It's so interesting, actually.
Yes. It's not sir. I'm Sujit. Yeah, we have an August guest, so you can see my screen. So I'll go to the just go back to the slides.
By the way, Riti also presented one thing. She's the lady entrepreneur here, and she is also
very
a
nice.
very good one. She also presented. I also share her presentation to you, and also share your
Yeah.
presentation with her as well.
Thank
And
you
she is
so
also
much,
doing
sir.
something.
Sure,
like
no
it.
problem.
Thank you.
Thank you so much.
So, are you talking about this slide?
The previous one to this, the hierarchy, this is one. Just go to the previous slide.
This one.
Yeah, this one. Electrical system, just 1 second. Because we have similar problem. I am sure I'll get a lot of inputs from here. Thank you so much, sir. But that's very
Yeah, so
small, but
basically-
can you explain?
I know
this,
it's
sir?
yes. So I can spend 1 or 2 minutes explaining. So to apply AI and bring predictive maintenance and the demand system with RCAs, you have to structure and digitalize things. So for the truck, you have to create a hierarchy of the way you approach the problem. So for this electric truck, we had components like the current collector, the field generator, the transformer, service motor, battery, current control. And then for example, the current collector, what's involved in the current collector? The carriage assembly, the collector arm, the proximity switch, same thing with the transformer, the service motor, battery, and then the field generator. These are components of the truck which we have presented in a structured format, so it is easier and amenable to AI analysis. That's all this is.
And did you put
Have
any
I answered your
bias?
question?
Yes, absolutely. Did you put any bias or any weight on component-wise or subcomponent?
Yeah. Actually, what we did is, before we did that, we did this thing actually. This one. We did a breakdown analysis, frequency analysis. So as we know, this high voltage electrical system was mainly main cause of breakdown, the blue system. So we put a bias on this system. So when we were analyzing that. So and you see the collector was one of the biggest problem areas of the electric truck. Collector is the way you transmit current from the bus bars to the drive systems of the truck.
Okay.
The collector is the overhead catenary system. This was a big problem. Like in light rail systems, also the same thing. The collector is the overhead catenary system is one of the big problems. The next one was the drives, the actual electric drives that power the truck. So we looked at this and then put a weight depending on this distribution.
Yes, I got it, because this is all coming from different suppliers, and the more failure areas probably you'll give more bias, right? You need to put
Yeah,
more.
exactly.
Got it. Okay. Thank you so much. Yeah.
No problem. Anything else before I stop sharing? Anybody else?
Good afternoon from India. I'm Dhruvo Bhaduri. Sir,
Yeah.
I have one question, that is,
Yeah.
like in this emerging technology, which is highly dynamic, new
Yeah.
technologies are being used, especially in the steel manufacturing. Now, what
Yeah.
is the system of skilling your workmen who are at the plant level? Because they have to upskill their whatever they have. So, do you have any policy for skilling your workmen, or what is it that you follow for upgrading their abilities?
In US, Canada, and Europe, the technician training and expertise and certification is highly regulated, and we do not have a good union is very much involved in it, the union of the workers. So they are not only certified, and they are also trained, and the government funding and the industrial funding is channelized through unions. And this is very different from India. In India, there is a combative attitude between the union and the governments and the management. But I'm not saying all organizations, some organizations, but in the developed countries like the Europe and Canada and US, the unions work with the government, the research institutions, and the certifying agencies. For example, I work as a professional engineer in these jurisdictions, and I have to be and legally authorized to work. So I have to do my certifications to achieve that. So it is a little different from India. Like in India, engineering is not a regulated profession, and technicians, they are not regulated. So the certification requirements are not that stringent, and the training requirements are not that stringent. But in Canada, Europe, US, it is a very stringent requirement in terms of certification and training. And there are colleges, universities. For engineers, it's the universities. For the technicians, it's the colleges where they have to go through training and certification. There's something called RATESIL. We call it something RATESIL certification, which is very important for technicians. Like if you're an electrical technician with RATESIL, it's a huge achievement. So that's the way it's done.
Okay, thank you, sir.
Thank you. Thank you. Okay. Else before I let you guys go.
Thank you, Sujit. It's an excellent presentation and a lot of appreciation. I think he needs a big hand from the people audience. Thank you,
It's-
thank you. We'll catch up.
Thank
We'll
you.
catch up.
It's
Yeah.
Yeah, it's my pleasure to present in this conference and meet everyone there. I've now been 30 years away from India, so I really have a nostalgic feeling about India. So any project that comes out of all this we'll be more than happy to work on.
Yeah,
Thank you.
We'll catch up. We'll catch up with the one research and things we are mentioning. We'll try to do. And now the last word from Rajiv De, Dr. Rajiv De. He is chairing the session, and I'll give it to him.
Thank you, Mr. Sengupta, for this excellent presentation. Really, this is the call of the day type of presentation, because these things we have to do it in the current future, because we have to go green. So thank you. And so with this, I end this session, because this session is over. So now I hand it to the Mr. P.K. Sen for the final valedictory session.
Yeah, thank you, Johan. Thank you, Sujit. And before you go for the valedictory, I may now call upon the stage the presenter here, that presenters, and also Rajiv, the chairman of the session, will felicitate. Yeah, Vibhor, I think Riti madam is here, and Vibhor, Sanjay, where is Sanjay? Is he left? Just see, Sanjay. Yeah, please come. And before the valedictory, there is some feedback form given. We value your feedback for your next conferences. Kindly fill it up and give it to that. Yeah. And now may I call upon Mr. Jayanta Chatterjee, because anyway you have to go to the stage. If you kindly do the favor, honor. Come. After that, you need to come down till the time valedictory. Now, come. Yes. Yeah, children. We can take a ফোনটা থাক না, কিছু কেউ নেবে না, এইখানে আস্তে করে উঠুন, আস্তে বাহ, come from here. Yeah, if you kindly come in front, please. Madam, please come first. She'll be happy to, yeah, fortunate, yeah. So more small token of your আসুন. Yeah. এইটা না, একটা করে দিন, একটা করে দিন, এইটা একটা। Yeah, thank you very much, thank you. এটা একটা। Thank you. Now next, can I call upon, please? Yeah, Mr. Sanjay Thakurdas, he is from IBM. He is always a pleasure to have presentations from Mr. Sanjay Thakurata. He has been here thinking out for things. Thank you. Thank you. Now, Bibor, please. Bibor, I am sure, after Mr. Vinod Sharma, that you are the one who are after this one. He was always talk very high about you. Now to our esteemed chairman and also member of the editorial board of Steel Tech, Dr. Rajiv De. Thank you very much. We'll have a group photo together for this one. Please keep the one and keep it. John Dada, apni jaben na, valedictory airport theke jaben. You need not to go down. We'll give you more punishment. Yep.